Hello, welcome to the third section for Unit 1. In the previous two sections, we were looking and focusing on vectors, dot products, what we do with individual vectors, operations, etc. In this lesson, we begin to actually dig into what linear algebra is mostly about, which is matrices. A matrix is a construction of vectors. Typically how you can look at it is column vectors or row vectors, either way. But more specifically, you can think about a matrix as an M by N rectangle. You can think about it as an array is another terminology you kind of see, especially in computer science. It's data placed specifically in kind of prettily, it's not really a word, but you know, whatever, it looks pretty. There we go, I guess that's the best way to kind of say it. So that all of the entries are in lines and organized like so. So let's say we had something called the identity matrix, which kind of referred to in previous videos, specifically looking at what is referred to as a 3 by 3. This is a 3 by 3 matrix. And it is called the identity matrix because along the main diagonal we have entries of 1, where there are 0 entries above and 0 entries above, or and below, excuse me, the main diagonal. This is called the identity matrix. We're going to learn a couple of really important relationships with the identity matrix later, and this is ultimately going to be one of our targets when we're reducing matrices, trying to solve equations, which we'll see in the next chapter. Etc. But this is an example of a matrix. In the Unit 0 notes, you're going to see a lot more terminology, ways that we notate a matrix, how we talk about the entries, etc. So I'm not going to go into great detail, other than M designates the number of rows, N designates the number of columns. So we always kind of view this in terms of 3 by 3. When we're looking at a matrix, specifically in that order. Even when I look at a vector, we look at it in terms of rows versus columns. So when I give a vector, let's say a vector x, typically I would list this vertically, which you've seen me do already, and I would refer to this as a 3 by 1. So a matrix doesn't have to necessarily have multiple columns. A matrix can be constructed of only one column. It's kind of the trivial case. The smallest you could go is essentially a 1 by 1, but there's no decimal columns, there's no decimal rows, etc. So we'll come back to a vector like this a little bit later, but our focus is going to be around matrices. Now there are some types of special matrices. Another name for this type when I have a 3 by 3, so an M and N are the same. You can refer to this as a square matrix. And the textbook gets into a couple of other square matrices that ultimately we'll investigate later on. So there is what's referred to as a diagonal matrix, diagonal matrices, is getting into the plural. Where, as you can imagine, if I have a square matrix, I might only have numbers along the main diagonal, so something like 2, 4, and 5, and then all of the other entries are 0. So you'll notice the identity matrix is a diagonal matrix, but every entry along the diagonal is 1, so a unit and identity piece. So if it's not 1 along the main diagonal, or there are no ones but other numbers, we call that a diagonal matrix. Another very important matrix that we will see is what's called a triangular matrix. These are going to play a huge role later as well, where a triangular matrix is all about the non-zero numbers creating a triangle with the main diagonal. So for example, I guess I'll rewrite it here. I was thinking about erasing this one, but I'll leave this up. Let's say I have 2, 4, and 5 along the main diagonal again. If I have zeros underneath but non-zero entries above, I can call this an upper triangular matrix. Upper in the sense that all of my non-zero entries are above the main diagonal. A lower triangular matrix would have the opposite of that. Essentially only 0 entries above the diagonal, non-zero entries below. So we can designate upper versus lower. Again, this example specifically is an upper triangular matrix. The last one, which again is going to be interesting, that we'll dive into a little bit later, is what's called a symmetric matrix. Again, we'll kind of see some important properties of these later. A symmetric matrix is all about symmetry across the main diagonal. So unlike the triangular, where if I compare entries along this, that does not have a mirror image, there's no symmetry there. For a symmetric matrix, they would, right? Given the fancy name of this. This entry here would be 1, this entry would be 1. If this upper right is -3, the lower left has to be -3. If this entry is 7, then this entry is 7 as well. So in other words, we have this symmetry kind of perpendicular to the main diagonal, if you want to think about it that way. You can think about functions, etc., with inverses, things like that. Just in terms of visually speaking of what makes a symmetric matrix, but pretty easy to identify what those are. The text also gives another example of a 3x4 matrix that I do want to put up on the board because it's one that he references throughout the next couple of examples, so I want to be able to point that one out as well. It also gives you a rectangular matrix, so it's one that's not a square. So this is an example of a 3x4, essentially meaning that, again, we have m is 3, or rows specifically. 4 is dictating my n variable or parameter, and this is dictating the number of columns. Now, what's going to be really important overall is we can dictate dimensions, how many terms are within the vectors, specifically number of components, the dimensional space is kind of what I want to make sure I gave you the correct wording. And so this 3x4 he references as A, so I'm going to do so as well because I kind of follow along with that notation in the textbook. I'm even going to go ahead and list out the entries. So he gives a -1, 1, and then 0, 0, 0, -1, 1, 0, and then -1, 1 to finish it off. And one of the highlights that he does with this matrix, and I would like to as well, is that we can view this matrix specifically in terms of columns. So because we're calling this matrix A, I can actually view this as being constructed as A1, A2, A3, A4, because I can't count. And so this matrix is constructed of these columns. And so you'll notice that the number of columns that we have matches my dimension for n. So there are 4 columns, but I have a dimension of 3 in terms of my rows. So we're essentially working within a 3-dimensional space, but I have 4 total columns listed, 4 vectors in 3-dimensional space. Now he gives a specific name to this, and I'm going to point this out as well. This is known as a difference matrix. And one of the reasons why he is using this, just to kind of give some background if you're reading through the textbook, is that he's going to use this as the instrument to talk about the row picture and the column picture of how we multiply a vector and a matrix together. And this is also going to help then bring in the conversation of independent and dependent vectors. aka we're looking at the column picture, we're going to be looking at A1, A2, A3, A4. So it's kind of driven through this idea of, what does this matrix do if I was to multiply it with another vector? aka how do I multiply a matrix and a vector together anyway? And how does that interact with one another? And that's kind of the question again. If I want to take a matrix, in particular this A, and I want to multiply it by another vector x together, we want to know what this looks like and how to work with this. Now, a couple things that we need to keep in mind is when I'm multiplying these 2 things together, if I list them quite literally, -1, 1, 0, 0, 0, -1, 1, 0, 0, 0, -1, 1. X is constructed of x1, x2, and x3, and x4. x1, x2, x3, and x4. In other words, the dimension on X has to match the number of columns in A. One of the ways that I like to remember it, my linear algebra teacher used this, my algebra teacher used this. If I was to list out the dimensions for matrix A, this being a 3 by 4, the dimensions on this vector are 4 by 1. See how these inner dimensions match? They have to match if I'm going to do multiplication. Whether that's matrix to matrix multiplication or matrix to vector multiplication, the number of columns in my left-hand matrix or vector needs to match the number of rows here. And part of the reason is how this multiplication is defined. Specifically, we can see it when we look at this through the row picture of multiplication. So if I'm trying to multiply these two things together, if I think about this in terms of the row picture, what I'm doing is I'm taking this row and I'm multiplying it with this column of the vector. So you'll see that I get -1 times x1 plus 1 times x2. And then I get 0 times x3. And I'm going to write this out. There's a reason. Plus 0 times x4. Well, what I want you to notice based off of our previous lesson in section 2 is that this is the dot product. Specifically, this is the dot product of taking row 1 and dotting this with x, my vector x, because I'm taking every entry in this first row and I'm multiplying it with its corresponding entry in my column vector of x. So when I look at the row picture of multiplication, again, we are doing a dot product calculation. And I would need to do this for each row. So I would do this again for row 2, dotted with x. I would do this with row 3, dotted with x. And my answer when I'm walking through and doing this now is a construction of a 3 by 1. So the outer dimensions actually tell me my final answer, what it should look like, is notice that it is going to be x2 minus x1. Here I would have x3 minus x2. And then finally, x4 minus x3. I apologize about the coughs. Everybody's getting sick. This is essentially right after Christmas break. But just to point out, again, that why this is called a difference matrix, it is because we are subtracting or finding the difference between these entries, subsequent entries, 2 and 1, 3 and 2, and 4 and 3, when I'm pairing them up. But this is the row picture. And you know, Dr. Strange, all right, there might be a little jump here, I apologize. The reason is I had a notification hit, so it paused my video. So I'm restarting the video and picking up right after we were talking about the differences in these entries, why this again is called a difference matrix. But we see our result here. Now again, this is called the row picture. It is using dot products. Now, when we are doing matrix in vector multiplication, Dr. Strong gets into this. It's personally how I was taught and how I think as well. And so I think many people, if you were to talk to them about multiplication, this is mostly how we think. If I was to do calculations, we typically think about calculations this way. If I had numbers for x1, x2, x3, and x4, I'm thinking dot product. I'm going row, column, row, column, row, column across the board. And then adding up those numbers and doing the algebra. Now, the thing that I like about how this material is presented and why I kind of chose this textbook is that there is another way to think about this multiplication, which is the column picture, which is mentioned, which we mentioned at the very beginning, back in the very first lesson, is that the column picture will give me a better idea of what this matrix can do and what it can do when I'm multiplying with any other vector. In other words, we can define more of what's referred to as its column space. We can find more information about what its rank is. We can find more information about are the columns independent or dependent? And what does that tell me? And all of those questions are essentially the reason why this course exists from this point on. We're trying to identify these connections and how do I solve these problems and what happens if I'm consistent versus inconsistent, and trying to answer those questions while honestly beginning to ask more questions and fall into that linear algebra rabbit hole. Now, the idea of the column picture is that instead of doing a bunch of dot products, we're going to be doing the same amount of calculations, but this time what I'm going to be doing is thinking about how I'm working this column times x1, plus this column times x2, this column times x3, this column times x4. So instead of doing the individual dot products 3 times, we're almost looking at it as one big picture. So just to kind of write out what that looks like, using the column notation from above, because now we're referring to it as A1, A2, A3, and A4, I can look at this as AX is equal to, and change this, A1, A2, A3, and A4. I can rewrite this now as X1 times A1. I can say then plus X2 times A2, plus X3 times A3, plus X4 times A4. We're now looking at a linear combination. And it's not the linear combination of just 2 vectors, it's the linear combination of all of the column vectors in my matrix of A and how they can interact with one another. And so this is the column picture. So again, the column picture shows us linear combinations. The row picture shows us a bunch of dot products. The number of calculations is about the same, if not the same. I feel like there can be differences, specifically in computer programming. If you had to program some way to solve these, when we get into later, there's better, more efficient ways to solve than what we would look at by hand. But this is the idea. And so if we want to look at this as the column picture, this is almost the preferred method and how we can begin to identify what this multiplication looks like, what this matrix essentially represents when I'm digging into problems and thinking about what we were looking at last lesson. Specifically speaking, and he puts this in bold, we want a picture of what every combination looks like. So like I could pick numbers for x1, x2, x3, and x4. We can choose a specific vector of x, and then we can see what the matrix A does to it when we're multiplying. But I want to know, what does matrix A do to every vector? Does it take every vector and put it into a line? Does it take every vector and put it into a plane? Does it take every vector and put it into a subspace of some larger dimension, 4, 5, 6, 12? Graphing becomes a harder issue once we get into those realms. But that's the idea of looking at a problem more so in terms of these linear combinations than necessarily doing a bunch of the dot products. Now again, the dot products, more so how we do this if we're actually performing combinations and we care about what that final answer looks like. But if we're just trying to get a picture of what this multiplication looks like, what A does again to vectors, we're going to choose this column space method, this column approach a little bit more than the row approach. Now, through this, because we're talking about linear combinations, the idea of independence and dependence now crops back up. And so that is the next kind of things we need to define and where this lesson and this video set will essentially end. We want to, again, start to discuss this idea of independence versus dependence. And he gives 3 really good examples in the textbook that I'm going to essentially go over. The first one outlining independence in the vectors of the column vectors of matrix. So he denotes this matrix as A1. This is example 1, where he calls matrix A1. I apologize, right there. Column vector 1, 2, 3. 0, 4, 5, 0, 0, 6. I should have been able to just do that one from memory. Now, what we're going to do with this matrix to see if they're independent or not is essentially start by reading this matrix from left to right. And if I'm starting with just one vector, I think we can agree that this vector has no other vector that can be a combination of it. So essentially your first column vector is always our good starting point, and we always start with at least one vector. Now, when I move on into the second vector, what we need to look at is there a combination of this first one that can give me this second vector? In other words, is there a multiplier, because there's nothing else to add with this one yet, that can get me to this vector? And you can clearly see the only way to get from 1 to 0 is by multiplying by 0, which essentially destroys everything else. AKA, this vector 0, 4, 5 is in a different direction than 1, 2, 3. It is a completely different vector. If this vector was a combination of this one, it has to be a scalar multiple because it's got to be in the same direction. It's got to be the exact same vector. There should be some scalar that we can use to get there, and we'll see that in the next one. Now, when I introduce a third vector, and you can kind of see how this gets more and more complex, now we're looking at this third vector and asking ourselves, can I do any linear combination of these two first vectors to get this third one? If I can, then these two vectors are independent while this vector is dependent. If I cannot, then this is also a new vector going in a new third direction, and then I have three completely independent vectors. So one of the ways that we can think about this is that if I took this matrix and I multiplied it by a vector x, if I was to trying to get to 0, the only way that I could get to 0 is if x was 0. If this is the case, then I can say that the column vectors of A are independent. And this is something that we're going to see kind of play out in the next two examples, is that we can get to 0 by using some other combination of vectors. In this case, there is no other kind of combination. Each of these vectors, because they go in each a different direction, fills the entire space of R3. Now, a couple of things that we can say with this then is because these are three linearly independent vectors. Independent, can't spell. Let's see, columns. Then these three columns are the column space of A1. And this column space is R3, because every combination of these three vectors would create the entirety of the third dimension. In other words, I can get to every single point. It covers the entire space of R3. We can abbreviate this by using CA. This refers to as the column space. And when you read column space, you need to think linearly independence. The dimension of the column space, the vectors that go in the column space, are created by taking the independent vectors from your matrix. So again, here, because I have three independent column vectors in the three-dimensional space, my column space is all of R3. They're all independent. I cannot come up with any combination to equal one of these individually, whether that's reading it from left to right or right to left. So these are all linearly independent. No column is a combination of any previous ones, as a way to kind of look at that. If we look at a second example, so we start to see, okay, well, what happens when this breaks down? So I think it also kind of outlines a little bit clearer of how this process works. But hopefully you still feel the tension and that it's really, really messy. Like, there's got to be another way to kind of think through this, and we'll see that there is. At least more algorithmic, more procedural, is the second matrix. So here you're going to see that there is a column that is dependent. So let's say the second matrix is 1, 1, 6, 2, 4, 0, 3, 5, 6, like so. So if we're looking at column vector by column vector by column vector, starting reading from left to right, if I cover up these vectors here, Notice that again, this first vector is automatically independent. Right? There's no other vector that can give a combination of it, so we're done. When I transition to the next one, I want you to notice that this vector also is completely independent of this one. Right? There is no scalar multiple here that can get me exactly into that vector. Primarily, we can see that here. To go from 6 to 0, I would need to multiply by 0. And if you remember what I wrote earlier, that means those vectors have to be independent. Now, when I introduce the third one, this is where we can kind of start to see the combinations. That if I add the first two vectors together, we get the third vector. So this means that if I was to multiply a2 by a vector of x, again, it's going to continue to use x. I think he uses c's at some point. That's a little bit later on in example 3. But I'm going to use x for this one. When I do this multiplication, and I do x1 times 1, 1, 6, plus x2 times 2, 4, 0, plus x3 times 3, 5, 6. If I'm trying to figure out what combination would create zeros across the board, if I let x1 be 1, I let x2 be 1, and I let x3 be negative 1, see how I can get 0, my 0 vector as a result? And because of that, because these entries here for x don't have to be 0 for that result, that means that these vectors as a whole aren't linearly independent. One of these vectors is dependent or can be written as a combination of previous vectors. Specifically, we've kind of identified that if these two are independent, it is this vector that we're viewing as a combination of the previous two, and we see that combination here. In other words, I can rewrite it. A3 is equal to A1 plus A2. A3 is dependent on A1 and A2. And that's the whole idea of independence versus dependence. So I can look at these two vectors by going left to right. Notice that direction is very important. These two create my column space. So the column space of A2 are the vectors 1, 1, 6, 2, 4, 0 is one way that I could express that. Notice how it's two vectors in a three-dimensional space. So this would form a plane. So you can kind of see how, looking at the column picture, we can start to identify some really important relationships when this matrix multiplies with another vector. It's taking, it can essentially get as an answer any vector in this plane, but any vector that's not on that plane, remember that two-dimensional space in a 3D world, would not be solvable, like it would be inconsistent. So we're getting some really important information from that. All the combinations do not fill all of R3 like we've seen before, right? It's going to fill a very, very specific plane. And so, I mean, this is linear dependence. I mean, we can kind of see it in this case when one vector becomes, or one column is a combination. Now, I was talking about really specifics of going left to right. You can actually go the other way as well. You don't have to read it left to right. You can read right to left. What you're still going to end up in is still the same space. And that's what's actually really interesting with this. Because now I could take this vector and this vector, which are two separate independent vectors. I can create this one now as a combination. So there's another way to rewrite it. And notice that no matter what, there are always two independent column vectors. One vector can always be written in terms of the other. Notice I could rewrite this vector as a combination of these two. So it really doesn't matter which two we choose, so why not just go left to right in like our natural like reading direction. So that's how we essentially view this. Now in the third example, we'll see what happens in a kind of an extreme case for dependence for A3. And the matrix that is given is 1, 2, 5. And then I think this next one, 3, 6, 15. And then the last column, 4, 8, 20. Again, if I'm looking at this third matrix and I'm checking for independence and I'm going column by column, again, notice how the first vector is given for free. Like that is independent. But the second I go to this one, notice how that is a multiple of the first one. If I multiply A1 by 3, we get A2. If I take A1 and multiply it by 4, we get A3. So there is only one linearly independent column in here. So one linearly independent column. Because of this, cannot spell independently. Because of this, the column space of A3 is constructed of only one vector, 1, 2, 5. And what that's describing then is a line in R3. So if I was to multiply a vector by A3, it's going to essentially give me any answer that is along this line, and only this line. It's kind of the most simplest case when it comes to these multiplications and linearly independence when you have that single vector, no matter the size of the space. But it's what's different from the previous one. I'm kind of following that theme of in three-dimensional space, if you have 3 vectors that work, that fills up the entirety of the space. If you have 2, that creates a plane. If you have 1, that creates a line. And so we're only going to stay on that line. We're only going to stay on that plane, or we're going to be able to get to any answer that we want to get to. So again, it gives us some really good information about when I'm trying to solve this problem, in particular whether I'm setting it equal to 0 or not setting equal to 0. Because I know that there's only one independent column, there are ways to get to 0 without having x to be 0. And that's probably one of the biggest, really the biggest takeaways, I think, from this beginner, which is if we want to define linearly independent, it's all about this. If we want to define essentially the column space, it's all about this because it's all about linearly independence. And so that definition that he gives for the column space, what I've been referring to here, is the column space of a matrix contains all vectors AX, aka it's all possible linear combinations. And again, this is why if we care to know something about the column space, what we're identifying, it's the linear combinations, it's the column picture. So it's all kind of connected. So this rounds out the first lesson. And the second lesson, where I thought a natural divider would be, is we're going to start looking at the column space, and specifically the title is Thinking About the Column Space on page 21. We'll start diving into 2 other matrices, start introducing some newer words, some bigger questions. And as long as the video doesn't get too long, we'll be able to finish off this chapter in 2 videos, looking at what is referred to as rank, which we'll get into in a minute. So.